Hi, in this video, we're going to take a look at the residuals from a logistic regression model. And we're also going to look at a couple of tests to measure the quality of our model along the way. All right, so what we're going to do is I'm going to take my data, I'm going to build a logistic regression model, and then to see how things are going, I'm going to take a look at the residuals that I have. Now, the residuals are the difference between what I observe the truth and what my model predicts for that particular value. And we'll have residuals for our training data, our validation data, and our test data. And if I'm doing a project that is like prediction, I'm going to look at all three of those. So I'm not going to get into that aspect here, but I am just going to look at the types of different residuals. All right, so first and foremost, we have binary outcomes, and we're going to code these as either 0 or 1. And so that's the only possible thing. So when we look at the residuals, we'll be looking at the probability of 1, the difference between that and the actual true value that it should have been. Now, if I have a really good model, I'll have my predicted probabilities will be close to 0 or 1, exactly when they should be. And now remember that a logistic regression model will never truly give me actually 0 or 1. It will be asymptotically close, so up to machine accuracy, close to 0 or 1 potentially, but we will never actually achieve, from a mathematician point of view, 0 or 1. All right, so here is our model, and that the probability of a success or a 1 is equal to this fraction, or here I have my predictor variables being multiplied by coefficients plus an intercept, all inside an exponential, and here we have that. And so if I eyeball that, I realize that this number always has to be strictly between 0 and 1. If the value here is super, super large and positive, then the fraction overall will be close to 1. If this is super, super large and negative and large, then this will be close to 0, but not exactly equal to 0. All right, so what we're going to do, first and foremost, we're going to build a model to work with to explain the ideas. And so here I'm just pulling in the piping operations, setting it up so that I don't get too much stuff printed out into my face. I'm avoiding scientific notation here, clearing my workspace of any junk. And I'm going to use the chronic heart disease data set from the elementary stat learn package. And for my machine, my version of R, I had to go with an old version of the package to be able to upload it. And something I'm going to do as a little bit of data prep is I'm going to convert family history, which is a 2-level binary categorical predictor. I'm going to convert that to dummy variables of 0 and 1 on this step. All right, so now I'm going to fit the model. So I've got family history, type A personality, tobacco, cholesterol, obesity, and age. And we're using the binomial family. All right, so here I go ahead, I fit my model, and we can see that all but 1 is statistically significant. I can tell you if I remove predictor variables, obesity will become, if I remove other predictor variables from here, obesity will become statistically significant. It has a correlation with the others, specifically cholesterol and age, by the way. But I'm going to keep it in. All right, so the first thing I want to talk about is the chi-square test. Now, this really isn't a good test to use when I'm doing logistic regression, but this is such a common test to be used. A lot of people know this from psychology and education statistics and the social sciences, that I wanted to start with something that people will be more familiar with. And so the chi-square goodness of fit test. All right, what we're going to do is I want to check to see, are my predictions for 0 or 1 matching up to the truth 0 or 1? If I have a junk model, it would just be complete no correspondence whatsoever. So our default setting is that there is no correspondence whatsoever on this. Our null hypothesis is that there is no relationship between the prediction and the actual truth. Okay, so on this one, if I have a good model, I will reject the null hypothesis. If I have a junk model, I will fail to reject the null hypothesis. Here, if you don't reject the null hypothesis by a large amount, you have a junk model more than likely. All right, so this one, I honestly, if you're just doing passing like bare minimum quality statistics, your bare minimum logistic regression model, your goodness of fit test for the chi-squared is going to reject the null hypothesis. But a lot of stakeholders recognize this test. And since they recognize it and they're comfortable with it, it's good to present because they'll feel, oh, hey, I know what's going on. I understand what's happening. So therefore, I'm more likely to accept the results. People will accept your statistics more, your results, if you present stuff that they're already familiar with, and that's important. All right, so what I'm going to do is I'm going to get the predicted value. So here I'm getting the probability. So in generalized linear models in R, I put the prediction type to response to get the modeled probabilities. If I don't do that, it's going to be the length function version with the logit. So here I'm getting the probabilities. Now what I'm going to do is I'm going to say, hey, if the model probability is above 0.5, I'm going to say they have coronary heart disease. If it is below 0.5, I'll say, or equal to, I'll say they don't have heart disease. And then I'm going to make a table, and then I'll run chi-square test. Now, here, I built a model with the intention of detecting heart disease, off of this. And so if I don't reject the null hypothesis by a large amount, I probably have a junk model. And so the failure to reject is not as informative as, rejecting the null hypothesis really isn't a big deal on this one because we've set, it's like we stacked the deck to reject the null hypothesis. If I don't reject the null hypothesis, that I say that there's like no relationship between you, that's a big deal. And we need to shut down that model. All right, the next one is a Hosmer limit show test. This is, from my point of view, the most common hypothesis test for logistic regression. All right, what we're going to do is that we're going to, this is going to be like more specific than what I did with the chi-squared. I'm going to divide the observations into deciles of risks, and then I'm going to use the chi-square test to assess the fit. So I'm breaking up into deciles, and because remember, I have, for those model probabilities, they are, that's a continuous variable. And so it doesn't make sense to be able to just like categorize directly. Notice that previously when I did chi-square test, I had to convert things to zeros or one. I had to bin the values. And so here I'm binning by deciles instead of 50-50 or cut off of 50%. All right, so a small p-value indicates a lack of fit between the model and the data. Okay, so with a lack of fit test, my null hypothesis is that there is no lack of fit. And then my alternative hypothesis is that there is a lack of fit. So if I reject the null hypothesis, that indicates that there is a lack of fit. So what I want to see, if I have a good model, I'll see a large p-value. Boom, I've got that. Easy peasy, lemon squeezy. Now, something that's useful, now this really doesn't go along with the rest of the video, but I don't know where to put this in the series. So I'm going to put it here. Here we've got the pseudo R squared measurement. And so this isn't, basically I'm trying to do R squared like in regular linear regression, but for logistic regression. And there are tons and tons and tons of ways to compute this. And there's more on Wikipedia, by the way, if you want to dig into these. Some bunch of ones I've never even seen before. But from my experience, McFadden and then Cox and Snell would be the most common two. So here, McFadden's is, I'm going to take the log likelihood of my fitted model, divided by the log likelihood of the null model. The null model for this one is where I just have the intercept as the predictor variable. So here, I'm saying, honestly, I'm saying either everything is coronary heart disease or nothing is coronary heart disease. I'm just going with whatever is most common in my data set. So if most of my data was coronary heart disease, I would say the null model would say everybody has coronary heart disease. If the data had fewer coronary heart disease than not, then the null model would say nobody has coronary heart disease. The null model is we basically declare everybody has the same results, and we don't even consider the predictor variables. All right, so we take this ratio and we subtract it from 1 to get a pseudo R squared. And so, this is real nice. So here I'm going to fit the null model, and I'm going to use the log likelihood function, and then, compute the ratio, subtract that off from 1, and we get 0.2. All right. And so we can also do this again. So this is the manual way, so that you can see how to do it. If I want to, I can go ahead and use a package from R to do it for me real nicely. And boom, we get, the same result up to rounding. All right, so now let's think about residuals in logistic regression. All right, so to get the residuals, I'm going to use the residuals.glm function. So I actually don't call this. This is under the hood. What's going to happen is that I'm going to call the residuals function in R, and R will recognize that my object is a generalized linear model, GLM, and will call the residuals.glm function for me. So this is a method. This is how like a lot of the more sophisticated code or functions in R operate. All right, so the first one I want to talk about is the response residual. The response residual is the actual true value minus the model probability. All right, so that is as raw as it can get. We also call these raw residuals or response residuals. And so we know that these are going to be between 0 and 1 for that, or so from -1 to 1. Is our range of possible values. And so just to show you what that looks like on the histogram, here's what I have for that model that I built. And so we can see that we've got more negatives on the histogram than positives with a spike of just a little bit less than 0. Okay, and well, -1 and 1, those are my largest possible residuals. Residuals close to there are giving me an indication, hey, I want to double check that observation. Maybe there's something wrong with the observation. Maybe I made a mistake in building my model. Like this gives, I know where to look. Now, Pearson residuals, this is going to take the raw residual, truth minus model probability, and then we're going to divide by the standard deviation to put things on a consistent scale, so I can compare between like different models. I get used to seeing things from the same point of view. All right, so here the standard deviation is going to be largest when when the model probability is equal to 1/2, and they'll be smallest when p is close to 0 or close to 1. You'll notice that here I've got a degree 2 inside that square root on the model probabilities. And so it's going to look like it's a quadratic, and the variance will be 0 when if the model probability was perfectly 0 or perfectly 1. And so this takes into account how much variability we would have expected. So getting it wrong when we modeled 50-50. So if the model probability was 50-50, well, then I see 0, I see 1. We know that if the model probability was 1/2, I'm going to get an error of 1/2 no matter what I do. It's going to have to be that way because the actual true value is 0 or 1. When we go and we predict an extreme value, if my model predicts something really close to 1 and it ends up being a 0, that's a big deal. And so this can help us spot that. And so here we can see the larger values going far out to the right on this one. Now, working residuals, what we're going to do is instead of dividing by the standard deviation, we're going to divide by the derivative of the link function. All right, so I take my raw residual and divide by the derivative of the link function, that logit link function, at the modeled probability. And so that's just another way to rescale to make things more consistent. So boom, look at that. Look at how we have larger values. It will be easier to say, hey, which ones are really extreme on this one. Now, deviance residuals, these are pretty common to be used. They're a measure of how well the model fits each observation. and they can be positive or negative, indicating whether the model over-predicted or under-predicted. And so here, I would say this is probably after the raw residuals and Pearson, this is probably the most common one to be used. So you'll notice that here I have the model probability of 1 and the model probability of 0. And you can see that I've got this combination here on the actual true values. So here I'm just taking the true value with the model probability of 1, the other value with model probability of 0, like that. And so here we have that scale. Now, partial residuals, this is where we want to actually go into the individual predictor variables, the covariates, and just check the individual aspect. Just try and see, is there something going on with a particular column of predictor variables individually? And so here on this, I take my raw residual, but then I add in the column predictor times its predictor coefficients, and to plug that back in to see what's going on. All right, so for your homework, I want you to train a logistic regression model and go ahead and do the chi-square test, run Hosmer limit show, do pseudo R squared, and then extract the response residuals, and then turn that in on web courses. All right, well, that's all I've got for you. Life is short. Do math.